In this presentation, we will study modulus of the counter, and once we are done with the modulus, we can study how to count up to a particular value. These two things are very important and also very interesting at the same time. So first we will study the modulus, and in this, if I talk about a 2-bit ripple counter, then it is called as the mod 4 or modulus 4 counter. In the same way, if I talk about a 3-bit ripple counter, it is called as mod 8 or modulus 8 counter. So what relation we can have here? If I say n is the number of bits, then the modulus or the mod number is equal to 2 to the power n, where n is the number of bits. Now let's see if we have calculated the correct mod numbers for our 2-bit and 3-bit ripple counters. If n is equal to 2, then for mod number for a 2-bit ripple counter is 2 to the power 2, and that is equal to 4. So the modulus 4 is a correct word to say for a 2-bit ripple counter. In the same way, if we have a 3-bit ripple counter, the n will be 3, then 2 to the power 3 gives me 8. So we call 3-bit ripple counter as a mod 8 counter. I'm telling you this thing because when you face a problem of counter, then definitely most of the time they will use this word mod 4, mod 8, mod 7, mod 6, mod 5. So you must know what is this mod. Now if you remember from my previous presentations, I told you that the state is equal to 2 to the power n, and also the mod number is equal to 2 to the power n. So I can say that, or we can say that, the modulus of a counter represents the number of the state. So this is a clear cut and the final thing about the modulus. It is the state. Modulus will tell us how many states a counter is having, how many counts it's going to do. So for a modulus 4, we know that we have 4 states from 0 0 to 1 1. In the same way, if a mod 8 counter is there, it means there are in total 8 states, and that states are 0 0 0 all the way to 1 1 1, 0 to 7. So this is all about the modulus, and if you want to make a table in your notes, then you can do 2-bit up or down counter. If you're having a 2-bit up or down counter, then we can say that the mod number or the modulus mod is 4. It is a mod 4 counter. And if I have a 3-bit up or down counter, then I have the modulus equal to 8 that we have already seen here. And if I have a 4-bit up or down counter, then the mod is 16. So I will call it mod 16 counter, and you can see up or down counter is not going to affect the mod number because up counter and down counter both have the same number of states. For example, if I am talking about a mod 4 counter, in case of up counting, it will start from 0 0 and end to 1 1, and if I am talking about the mod 4 down counter, then it will start from 1 1 and end at 0 0. The number of states 4 in both the cases. So I hope you now know what is the modulus of the counter. Now we can move a very important topic, that is counting up to a particular value. How we can stop counting at a particular state or at a particular count or at a particular value, that we have to see. So please watch it carefully, and it is going to help you in so many problems relating to the counter. So let's start with our second part of this presentation. So let's take one example for this, and I want a mod 6 counter using mod 8 counter. So this is my question, and this you can see we have a mod 8 counter. This shows that I have a 3-bit ripple counter, because mod 8 is nothing but a 3-bit ripple counter. Definitely it could be a 3-bit synchronous counter, but we are talking about the ripple counter or asynchronous counter, so let's consider it the ripple counter only. And by using this 3-bit ripple counter, we want to have a mod 6 counter. So let's do some anatomy of this question. so that we can learn something very interesting. And in this mod 6 counter, we know that the total number of states is going to be 6, because mod is nothing but the number of states. And if there are 6 states, we know that the maximum count, let me write, maximum count is equal to 6 minus 1, and that is 5. So our counter that we want will start counting from 0 0 0, and then it will go to 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1. This first one is the decimal equivalent of 0. In the same way, we have 1 2 3 4 and then 5. So you can say that this is our mod 6 counter. It is starting from 0 and ending its count at 5, but we have to use a mod 8 counter. So how we are going to do this thing? For this, we need a mod 8 counter that I have already made here. You have already learned about this mod 8 counter, that is our 3-bit triple counter. In this particular case, when you have to count up to a particular value, we will use preset and clear inputs. I hope you have watched my presentation on this preset and clear input in flip-flops. If you don't, there is no problem. It's a very simple thing. I'm going to explain you right now. We have 2 overriding inputs in flip-flops. That is not generally shown in every applications because they are not required for that, but in this case we need them. I need a preset and a clear input, and in the same way we have the preset and clear input for the rest of the 2 flip-flops. Let's see what this preset and clear input does. They are the active low signal. By the active low signal, I mean whenever they are low, the flip-flop is going to be overridden. We have a specific output instead of the value of my clock or my inputs, that is JA and KA. Whatever be the value of JA and KA is not going to affect the output of this flip-flop. So let's see what is the effect because of the preset and clear input. If preset is a 0, the output, that is Q, is going to be 1. It is going to be set. And if clear is equal to 0, the output Q is going to be a 0. So this is the thing that you have to keep in your mind. If you want to reset your flip-flop, you have to make clear equal to 0. If you want to set your flip-flop, you have to make preset equal to 0. And this bubbles so that they are active low signal. It's not like we have used a NOT gate here. They are just a symbol to represent that it is an active low signal. They are in action when they are low. So I hope you know the use of the preset and clear input. Now in what way we can use this preset and clear input to count up to 5 instead of 7. If this is the counter, in general it will count more. After 5 it will count 1 1 0, that is my 6, and then finally 1 1 1. Now you can see we don't want these 2 states. We don't want these 2 counts. It is not required because we need a mod 6 counter. If it will count 6 and 7, we have a 8 mod counter, modulus 8 counter that we don't want. So as soon as the 6 is arrived, we want to reset our flip-flops, all these 3 flip-flops. So what we can do, we will use a NAND gate. Let's use a NAND gate here. This is my NAND gate, and I have used a 3-input NAND gate, and as soon as we have 6, it means if this one is my MSB, and MSB is definitely QC, this one, and this one is my LSB, and LSB is QA. So I have QC, then I have QB, and I will use a NOT gate, and I have QA. Now you can see when we have 6, it means I have 1, 1 and 1 here. QA is 0 in case of 6, and this NOT gate will make it 1. So this NAND gate will have output equal to 0, and this output will be given to all the clear inputs of the 3 flip-flops. So I will give the output of my NAND gate to all the clear inputs, and as soon as we have 6, the output is 0 and the clear is 0. And you can see when clear is 0, we have outputs at 0. So our flip-flop is now reset, and thus it will again have the output equal to 0. So we are counting from 0 0, we are going up to 5, and then we are again going to 0, because this NAND gate will make the flip-flop reset as soon as 6 is arrived. I hope you got this thing. Now let's try to have the output waveforms. First I will plot QA. I will use the concept of toggling. Whenever there is a falling edge, I will have the change in my circuit, and definitely I will have a toggling, because you can see this logic 1 is there and it is given to the J and K, and definitely I am going to connect my preset with logic 1, because I don't want the set action. I don't want the set action, so I will make preset equal to 1 so that there is no interruption from the preset. So this is the way to do it. And now we will plot QA. QA is low initially, it will remain low for the first falling edge, then again it will go high and again low. This is the toggling. You can see we have the complement of the present state, and in this way you can complete. Okay, now we will plot QB, and you already know QB is having the clock as QA, so we are going to consider QA as our clock, and the falling edges are this, and QB is also low initially, it will remain low for the first falling edge, it will go high then, and then it will go low again and then high. Now let's plot QC, and for QC, QB is my clock and this is the falling edge. It will remain low for the first falling edge, and then because of toggling it will go high. Now this is the case when we have the normal mod 8 counter, but in this case we have a mod 6 counter after the 6th clock pulse is detected, which means 1 1 0 1 1 0 is 6. We have a reset action, so I have to remove this portion. Okay, and we have QA as 0 for the next falling edge, and in the same way we have QB as 0 and QC as 0. So once we have the 6 clock pulses passed, we have 0 0 0. We are again back to 0 0 0. So this is how mod 6 counter works. I hope you got this concept, and if you have any doubt regarding the modulus of a counter or how to count up to a particular value, you can ask. Definitely I will use one more example to explain this concept, and this is only for the basics, and this is the circuit that we use. There is a use of preset and clear inputs. I have made preset high because we don't want any set action, we just want the reset action. As soon as 6 is arrived, we want to reset all this flip-flop, so I have used a NAND gate for this purpose. So this is all for this presentation. See you in the next one.